Okay, this project really this activity really is part of a project with another one on the ITH, or the Invicta Highway, ITH for short. One of the things that's driving it, there is actually a relatively limited understanding of how permafrost geochemistry differs from that in non-permafrost areas. So this project will address that bit of a knowledge gap, and more importantly, what the environmental risk is for that geochemistry poses. And as you'll see, there's some fairly strange geochemistry around the ITH. One of the things I really want to look at is the seasonal hydrology, because it's a relatively radical hydrologic cycle up in the far north, and so that must have some impact. Though again, as I said, there's a lot of we do not understand. Next, please. A whole bunch of partners, First Nations partners, Department of Infrastructure for the Northwest Territories, Environment Canada, and our own colleagues here at GSC. Next, please. Okay, I'm just going to go through this. This was the sort of starting point for this, where I looked, went up there and did some looking at the permafrost and the active layer geochemistry. The ITH is in the foreground on the bottom left there, marked ITH, and if you actually do it, and I did a transect of groundwater samples across there, and you can see that it goes, the depth of permafrost increases to the left, getting to a maximum of 1.1 meters. Next. Now, if you actually put the chemistry on top of that, you'll actually see that it's all pretty high chemistry, and where that subsurface channel is, it has extreme geochemistry. 16,000 microsiemens per centimeter electrical conductivity, aluminium at 14,000 parts per billion. So that's about 1,400 times aquatic guidelines. It's in a cold temperature environment with limited hydrologic cycle. That makes no geochemical sense. Next, please. And if you actually look at the sediments coming out of there, there's these orange goopy sediments coming out of that 1.1 meter groundwater sample. And again, something's really destabilizing those clays and minerals within that profile. Again, not what you should expect from a cold temperature site. Next. So this is sort of the instigator of this project, is extreme geochemistry. What environmental risks do these high contaminant levels indicate? And there's clearly some subsurface pathways. What is the surface groundwater linkages? We just don't know. And that goes on to where we will actually really focus our efforts in the next slide. As part of the ITH, they actually had to get a whole bunch of gravel, and so they made these borrow pits. And in these borrow pits, there's now sumps, and as you can see, they actually drain out of these borrow pits. And some of these sumps are really toxic. They've got antimony, aluminium, zinc, copper, uranium, mercury. It varies depending on the pit. Not all is the same. All the pits have different sets of the same suite of contaminants. But nonetheless, as you can see, they're right next to water bodies. What's happening to those contaminants, we really don't know. We just have no groundwater data. We have a limited amount of surface water data. But they're a great target to research, because essentially there's high contaminant levels, and they are draining out of those pits. So we've got a point source, and we can start looking at them and seeing how we can follow them through the environment. Next. And that's pretty much what we're going to do. And we're going to figure out some process geochemistry on these things. What are the sources? What are the transportation? What are the fixation? What is the hydrologic overprint on these? And therefore, what kind of environmental risk do these things actually represent? Is it just not moving very far, or is it actually moving into the water bodies, getting into the food web, or whatever? We really don't know. But that is a good place to start and look at the process geochemistry and the environmental risks that follows. Next. And that, in a nutshell, is that. Any questions? Feel free to contact.
Thank you, Paul.